conductance. So I can say R is equal to 1 by K into L by A, where K is called specific conductance. Or it is called conductivity. And RK is equal to L by A. Can you see it, sir?
Yes, sir.
Sir, this L by A is fixed for a given cell, sir. If you are taking any damn cell, the length of this electrode and the cross-sectional area of this electrode will remain the same, whatever the liquid you take inside. Yes or no? Hello?
Yes, sir.
Because it is constant for a given cell, I call L by A as cell constant. So always cell constant is equal to what, sir?
Resistance into conductivity.
It is equal to Mr. Ramakrishna or K. Or you can say Rahim Khan. L by A is equal to Mr. Rahim Khan. You have any problem?
No, sir.
Hello? So you remember that cell constant is equal to Rahim Khan or K. If you know cell constant, if you know the R value, you can find specific conductance. Yes or no?
Yes, sir.
Yes, sir.
Now, ladies and gentlemen, we also agreed upon that the conductance offered by all ions which are present in a given electrolyte, it may be 1 liter, it may be 100 liters, it may be 1000 liters. If it has 1 mole, conductance due to all ions offered by 1 mole of electrolyte dissolved in given volume is called molar conductance. What is it called, sir?
Molar conductance.
Sir, what do you do? One thing. Yeah. Sir, what is this diagram?
Wheatstone bridge, sir.
You know P by Q is equal to R by S at a null point. Do you know it is Wheatstone bridge?
Yes, sir.
Using a Wheatstone bridge, if you know the resistance of 3 resistors P, Q and R, you can find what is the resistance of S. Yes or no?
Yes, sir.
There in the Wheatstone bridge, you are using the DC, direct current. Now, sir, you want to know conductance of this solution, which you don't know. To know the conductance of this solution, oh, it has gone well. I will try again. So you have, instead of one of the resistors, you kept the wires open in a solution. The solution resistance you can measure using the same relation. Yes or no, sir?
Yes, sir.
But unfortunately, when you are taking a solution, sir, I request you don't use DC. If you are using direct current, what happens is the electrolyte will undergo electrolysis. So the concentration of the solution keeps on changing because of chemical reaction. If you don't want chemical reaction, you should use AC, alternate current. Alternate current is used to maintain the concentration of solution and to prevent the electrolysis. Sir, when you are using AC current here, you can't use jockey. You can use what is called ear pods. At a null point, ear pods will make a sound. Gwee. When the ear pods are making a sound, you by adjustment, you understand null point has reached. At null point, P by Q is equal to R by S. You can find the resistance of the solution, and 1 by resistance is equal to what, sir? Hello.
Conductance.
And that conductance corresponding to a solute which is there 1 mole in a given volume of solution. Maybe it is 100 ml, maybe it is 1000 ml, maybe it is 10,000 ml, I don't care. It is called molar conductance. Ladies and gentlemen, if I dissolve one equivalence of a given electrolyte in 1 liter or 2 liters or 100 liters, conductance due to all ions caused by that one equivalent mass of solute in a given volume of electrolyte is called equivalent conductance. You know, molar conductance is equal to specific conductance into volume of solution. But volume of solution is also equal to 1000 by molarity. Similarly, equivalent conductance is equal to Kv is equal to K into 1000 by what, sir?
Normally.
Sir? Ladies and gentlemen, you know that K is having a unit of Siemens per centimeter. Do you remember, sir?
Yes.
Yes, sir.
Sir, molarity is having a unit moles per liter or moles per centimeter cube. Agreed, sir? Because 1000 centimeter cube will make 1 liter. Hello.
Yes, sir. Agreed.
So I will say it is in the denominator, centimeter cube when comes up will become centimeter cube and mole inverse. It is Siemens centimeter square per mole is the unit of molar conductance, or you can take also it in Siemens meter square per mole. Please notice 1 meter is equal to 100 centimeters. Therefore, Siemens meter square per mole is equal to 10 to the power 4 into Siemens centimeter square per mole. That is the unit of molar conductance. Instead of saying Siemens centimeter square per mole, you can say Siemens centimeter square per equivalent mass if you are taking one normal solution. Are you clear, sir? Hello?
Yes, sir. Clear.
Sir, somebody is giving you the value of the resistance offered by a conductor. Somebody is also giving you the value of cell constant. Can you find K, sir? Can you find K, sir? Hello?
Yes, sir.
You found the K, no, sir? Once you know the K value, can you find the molar conductance using a relationship? Molar conductance is equal to K into 1000 by molarity of solution. You have any problem, sir? Hello?
No, sir.
No, sir.
Sir, for one particular solution, they are giving you specific conductance and resistance. And in the same cell, they are taking a different electrolyte. So for the different electrolyte, L by A value will be same, no, sir?
Yes, sir.
When once you know L by A value, cell constant value from the first set of experiment, in the second set of experiment, you use the same L by A value. And if you know the resistance of this particular solution, can you find its specific conductance?
Yes.
Yes, sir.
Once you know its specific conductance, can you find its molar conductance?
Yes.
Once you know the molar conductance, now you can plot a graph how the molar conductance varies with respect to square root of concentration. That's what a gentleman called the Debye. That's what the gentleman called Arrhenius has done. Arrhenius noticed that the solution has shown a conductance like this at a particular concentration. Now he added water. When he has added water, its concentration increased or decreased, sir? Am I going in the right side or am I going in the left side when I am adding water?
Left side.
Concentration increase.
Left side, sir.
I am going towards red or I am going towards blue?
Blue, sir.
Sir, I add some more water, sir.
More
I
left
add some more water, sir. It means by adding water, I am decreasing concentration, sir. Are we very clear?
Yes.
When I am adding water, when I am decreasing concentration, when I am increasing dilution, I notice conductance is doing what, sir? Increasing.
Increase.
Sir, if I extend this graph, up to this point. At this point, what is the concentration, sir? Yes or no?
Yes, sir.
Hello. It means that when the concentration tends to zero, the conductance is showing highest value. The conductance shown by an electrolyte at a very diluted state, the maximum value is called molar conductance at infinite dilution. What is it called, sir?
Molar conductance at an infinite.
The Arrhenius got surprised. Why the hell overall conductance? No doubt. Specific conductance in 1 centimeter cube volume is decreasing because number of ions are decreasing. But overall ions are freely moving as I am adding more and more water. Therefore, when I am adding water, when I am decreasing the concentration, I notice that the conductance is increasing and increasing and increasing. If I extrapolate, I am getting a certain value at the highest point. Intercept is called molar conductance at infinite dilution. Are we clear, sir?
Yes.
Yes, sir.
Then Arrhenius made a relationship that the molar conductance at concentration C is equal to molar conductance at infinite dilution minus what, sir? B root C. What is B, sir? What is B, sir? B is a constant. What is B, sir? Hello?
Constant.
Constant.
So this graph is looking like y is equal to minus mx plus c. Can you see it, sir?
Yes, sir.
How a graph y is equal to minus mx plus c looks like? It is a straight line with a negative slope. Yes or no? Hello?
Yes,
Yes,
sir.
sir.
Sir, how
And
a graph y
constant.
is equal to mx plus c looks like? Like this. How a graph y is equal to mx looks like?
Straight line from 0.
How a graph y is equal to mx square looks like? What is this, man? No, I don't go there. I will control my temptation. Okay, so let me not worry about it. So this is Arrhenius relationship. Sir, are we very clear? Now, when you practically plot this graph for KCl, for NaCl, it is like this. For MgSO4, it is like this. This is called univalent electrolyte because both fellows have plus charge. It is called bivalent electrolyte because it is 2 minus, it is 2 plus. Sir, what is this MgCl2? What type of electrolyte it is?
Biunivalent.
Biunivalent electrolyte. This is your acetic acid. Now, one important observation, a graph of square root of concentration versus molar conductance is a straight line in case of strong electrolytes, but the variation is very, very less with the dilution for univalent electrolyte. The variation is apparently more for a bivalent electrolyte. The variation is very strange for a weak electrolyte like acetic acid. Slowly it is increasing, but when the dilution reached a point, suddenly it started increasing. So the behavior of weak electrolytes could not follow the pattern as predicted by Arrhenius. Arrhenius said that there is a linear relationship for the relation between dilution and molar conductance. And if Arrhenius relation is valid, if I extend this straight line, I will be getting molar conductance at infinite dilution by extrapolating the graph. Is it extrapolation or interpolation, sir? Hello?
Extrapolation, sir.
And very interestingly, I tell you, this is what you studied in first year. If you have acetic acid, which is a weak electrolyte, is it dissociating 100%, sir?
No, sir.
If I am taking C moles of acetic acid, If alpha is the degree of dissociation, actually dissociated molecules are C alpha. I might have given you an example like a boy is selling chocolates. A 10, 12 years boy, when he was selling chocolates, a parcel boy like me inquired, oh boy, you are selling chocolates, very good. Cost of each chocolate is 10 rupees, fantastic. But don't you get the temptation to eat a chocolate? Suppose you got tempted to eat 5 chocolates. Then when you are paying money to your owner, evening, there can be a shortage of 50 rupees because you ate up 5 chocolates. For that, there is no money. And if it happens, don't you think that your master will scold you? What the boy said? Hello? You understand my problem?
Yes, sir.
A boy is selling chocolates. Cost of each chocolate is 10 rupees. They are very delicious because he is after all a boy of 10, 12 years. Naturally, he should get a temptation to eat the chocolate. When he eats the chocolate, say 5 chocolates, if he eats in a day, there will be a shortage of 50 rupees, which is unaccounted for. Won't the master scold him? What do you think? Hello? Will he scold him or not?
Yes, sir.
He will not only scold, he will kick nicely. Any doubt?
No doubt, sir.
Therefore, now what happens? The boy, then the gentleman asks how you are managing this scenario. The boy answered, sir, don't tell to anybody. What I do is actually, I open up the wrapper of a chocolate. I just lick it 2 times. And then I carefully keep the wrapper back and just mix in the heap. So, in every time when he opens up the wrapper and licks 2 times, suppose he eats 1/100th of a chocolate. And he sold 200 chocolates. How many chocolates actually he ate, sir? Can you see it, sir? Notice that now we make an equation. The acetic acid is there, which is dissociating very slightly. Now I have taken C moles and actually he sold 200 chocolates. In each chocolate he ate 1/100. How many chocolates he ate actually? He ate C alpha. C is 200, alpha is 1/100, 200 into 1/100, that is 2. C alpha will give me always C alpha will always give me the number of chocolates that have been actually eaten. That corresponds to the acetate ion concentration and a H plus ion concentration. Therefore, now what happens, sir? Okay. Now, the acetic acid left undissociated is C minus C alpha. The acetate ion formed is C alpha. The H plus ion formed is also C alpha. This is the state when the reaction sets, when the dissociation sets at equilibrium. Now what happens is, okay, sir. When acetic acid is taken in a container, when acetic acid dissociates, you get acetate ions and H plus ions. If I start with the C moles of acetic acid, if it is dissociating by C alpha, at equilibrium, I have C alpha acetate ions, C alpha H plus ions. So finally, we are left with C minus C alpha acetic acid ion, which is undissociated, C alpha acetate ion, C alpha H plus ion. Sir, if you want to know pH, do you know pH is equal to minus log of H plus? Therefore, pH is equal to minus log of C alpha. Notice, if I want to find the pH, I should know H plus. If I want to know H plus, I should know alpha. And alpha is actually degree of dissociation. Now, for a weak electrolyte, if I want to know degree of dissociation, I have one method. If more is the acetic acid molecules that are getting dissociated, more is the alpha. More is the H plus ions and acetate ions, more is conductance. Notice that when I am adding water to electrolyte, the conductance is increasing, means the ions are increasing. It means that the degree of dissociation can be said to be equal to alpha is equal to molar conductance at concentration C divided by molar conductance at infinite dilution. So if I know what is the molar conductance of a given electrolyte, if I can compare it with molar conductance at infinite dilution, the ratio between the molar conductance at concentration C and molar conductance at infinite dilution, that gives me degree of dissociation. If I know degree of dissociation, I can find the H plus as C alpha. I can also find the acid dissociation constant as C alpha square. So knowing alpha is very, very important for making many calculations in chemistry. What do you mean by alpha? Alpha means degree of dissociation. How to find the degree of dissociation? This is the ratio between the conductance of an electrolyte at concentration C and its conductance at infinite dilution. Are we very clear on this, sir? Now, this is valid for strong electrolyte, but Arrhenius equation is invalid for weak electrolyte. For weak electrolyte, if this variation is like a curve, I can't extrapolate. If the variation is like a straight line, I can extrapolate. Can you see? For acetic acid, it is varying like this. How can I extrapolate? Straight line means I can find. Therefore, to know the molar conductance at infinite dilution, for weak electrolyte, the relationship given by Debye, Huckel and Ansager is of no use. The Arrhenius relationship is no use. So I want a better relation. Now, how to know the molar conductance at infinite dilution for a weak electrolyte is a big problem. Ladies and gentlemen, we are talking about conductance. We agreed upon that conductance is reciprocal to resistance. Conductance can be measured using a Wheatstone bridge formula. Conductance of an electrolyte is dependent on nature of the electrolyte, because we have seen that univalent electrolytes, bivalent electrolytes, so on, Therefore, nature of electrolyte B means the electrolyte can be a strong electrolyte, it can be weak electrolyte, it may dissociate fully, it may dissociate partially, so on. In what material you have dissolved the salt? That is nature of solvent. Suppose if you are putting sugar in some oil, that won't conduct the current at all. If you are putting salt in water, it can conduct. If you put salt in alcohol, it may conduct less. Like that, nature of solvent also decides the conductance to some extent. Also, how viscous the solution, viscosity of the solution affects the conductance. What is the concentration of the electrolyte, concentration of solution? We have seen the less is the concentration, more is the conductance. So conductance depends on concentration. Also, it depends on temperature. Normally, for a solid wires, if I am heating, the conductance will decrease on heating. It means the resistance increases because electrons try to move in random directions. A wire will be a bad conductor of electric current if you are heating it. Whenever I am heating an electric wire, it will become a poor conductor. Its resistance will increase due to random motion of electrons. However, for electrolytes, if I am heating, ions can move fast. Therefore, the conductance will increase. So, the conductance depends on temperature. Conductance also depends on the size of ions. The size of ions is a very important idea, sir. I would like to say that I take lithium ion, sodium ion, potassium ion, rubidium ion, cesium ion. I am taking different ions in aqueous solution. Very interestingly, the smaller ions which have more charge can readily surrounded by millions of water molecules. It means they are hydrated. If you take these ions, lithium is excessively hydrated. Billions and trillions of water molecules will surround the lithium. When lithium ion is surrounded by so many water molecules, its size will be very bigger. As hydrated lithium ion becomes very big in size, its moment or mobility when you pass current becomes less. Therefore, lithium ion in aqueous solution is a poor conductor. When you are looking at cesium ion, the bigger the ion, the lesser is the extent of hydration. Therefore, the hydrated cesium ion will be much smaller in size than the hydrated lithium ion. That is the reason why when I am taking these ions, cesium ion is a better conductor than lithium. In gas phase, if I see, in gas phase, lithium ion is small, cesium ion is big. But in water solution, the story is just opposite. Therefore, the conductance of an electrolyte depends on many factors. Now, conductance is measured, which is termed as molar conductance, using a Wheatstone-Bridge formula. Molar conductance can also be calculated using a formula, the specific conductance into 1000 by molarity of solution. Equivalent conductance is equal to K into 1000 by normality of solution. Notice that molar conductance is equal to equivalent conductance into N factor. For example, for H2SO4, equivalent weight is half of the molecular weight. It means N factor for sulfuric acid is 2. Therefore, if you want to have the molar conductance of sulfuric acid, multiply its equivalent conductance with 2. For the aluminum chloride solution, N factor is equal to 3. In that case, molar conductance is equivalent conductance into 3. For NaOH, HCl, etc., the normality is equal to molarity, equivalent weight is equal to molecular weight because N factor is 1. For such case, both are equal. So that is another question normally we are encountered in this subject. We already noticed that molar conductance at concentration C is equal to molar conductance at infinite dilution into B into root C, where B is called a constant. Debye, Huckel and Ansager, these are the three scientists, Debye, Huckel and Ansager. These three scientists have developed this equation and gave the value of B as a constant. They arrived at its value 82.4 by eta into dt under root plus say 8.2 into 10 to the power 5 by dt whole to the power 3 by 2. What is this relationship they gave? We need not have to derive it, but I want to say that eta is viscosity coefficient. D is called dielectric constant. T is called temperature. What is B has been worked out by these scientists. Notice that viscosity can affect the conductance. Dielectric constant is a property of liquids. For example, if I am putting salt NaCl in water, Na plus Cl minus normally attract each other because they have opposite charges. Now, when they are attracting each other, if I put it in water, water molecules will go in between. When so many water molecules are coming in between, the charge attraction between Na plus and Cl minus is being cancelled by water. To what extent this attraction is cancelled is measured by dielectric constant. Because the Na plus Cl minus electric attraction is being reduced by water, the Na plus Cl minus gets separated. Therefore, salt dissolves in water. If you put salt in benzene, it will not dissolve because the attraction between Na plus and Cl minus is not affected by benzene. So dielectric constant of benzene is 0. Dielectric constant of water is 82.4. Sir, for heavy water, dielectric constant is 81. It means in heavy water, salt is less soluble than in water. So dielectric constant is a measure for the decrease in the electrostatic attraction between a positive and negative ions in a solvent. This dielectric constant can affect the conductance. So the relationship between the conductance, the dielectric constant of the solvent and the viscosity of the solvent has been given by Debye, Huckel and Ansager. In this relationship, they have found the value of B like this. More than this, we need not have to go. This is only for advanced. I am just touching this idea. Now, I have one very important and urgent message, sir. For any electrolyte, if I want to know alpha, I should know the molar conductance at concentration C and the molar conductance at infinite dilution. I must know alpha because if I know alpha, I can find, say, H plus ion concentration as C alpha. I can find pH. If I know alpha, I can find the equilibrium constant, which is given by C alpha square. So knowledge of alpha appears to be important to find many other things. And alpha is equal to molar conductance at concentration C by molar conductance at infinite dilution. Now, molar conductance at infinite dilution can be found for a strong electrolyte by extrapolating the graph. But for a weak electrolyte, I have no way to find molar conductance at infinite dilution. Now, most important part, Kohl-Rosch law. According to Kohl-Rosch law, the conductance of any ion at infinite dilution is independent of other ions. It implies conductance is at infinite dilution is additive. Sir, what is the meaning of it? Sir, I have NaCl. I added a lot of water. The Na plus Cl minus are getting separated. The conductance due to the Na plus ions at infinite dilution is not affected by conductance due to Cl minus ions at infinite dilution. It means that, sir, if I know the molar conductance at infinite dilution for NaCl, if I know molar conductance at infinite dilution for HCl, if I know molar conductance at infinite dilution for sodium acetate is a strong electrolyte, HCl is a strong electrolyte, NaCl is a strong electrolyte. At infinite dilution, it gives me Na plus ion, Cl minus ions. It gives me H plus ion, Cl minus ions. It gives me acetate ions and Na plus ions. Using these three informations, can I find the conductance at infinite dilution for acetic acid? I can definitely find the molar conductance of acetic acid at infinite dilution by adding 2 to 3 and subtracting 1. Can you see it, sir? Hello. If I add 3 and 2, I am getting conductance due to H plus Cl minus acetate ion Na plus. From this, I am subtracting Na plus and Cl minus. So, if I am subtracting, I will be getting acetic acid conductance. It means one can find the molar conductance at infinite dilution for a weak electrolyte using the data from strong electrolytes. Are we very clear, sir? For example, you want to know what is the molar conductance at infinite dilution for barium chloride. It is equal to conductance due to barium ions plus 2 into conductance due to chloride ions. This value, how can I get means, if it is a strong electrolyte, I can find it by using the direct experiment. If it is a weak electrolyte, I can take different electrolytes and I can either add or subtract or do some mathematical manipulation and get it. But always notice that molar conductance at infinite dilution for an electrolyte is equal to sum of the conductances of individual ions, which is not affected by each other. Are we very clear on this idea? For example, what is the molar conductance at infinite dilution of ferric sulfate? Fe2SO4 taken thrice. It is equal to 2 into molar conductance at infinite dilution of ferric ions plus 3 into molar conductance at infinite dilution of sulfate ions. For individual ions, I am using small lambda. For overall conductance, I am using capital lambda. It is also lambda, it is also lambda. Okay, sir, this is a representation we have. Sometimes they are using a term called ionic mobility. If I am taking NaCl as a solid, the Na plus Cl minus ions cannot move because they are in solid. Now, if I am putting the NaCl in water, now the ions can move because water is providing a facility to move around. The mobility of the ion means the conductance offered by each particular ion for the passage of 1 Coulomb charge. The mobility of an ion, for example, a positive ion is given by molar conductance at infinite dilution of that positive ion divided by 96,500 coulombs. I am dividing with 96,500 coulombs because I am getting one equivalent conductance for the passage of 1 Faraday. 1 Faraday means 96,500 coulombs. So whenever I want to have ionic mobility of any particular ion is equal to mu for any plus ion is equal to molar conductance at infinite dilution divided by 96,500. By definition, ionic mobility is the conductance offered by any particular ion for the maintenance of 1 Coulomb charge. That is another related idea about the ionic mobility. So in this topic, so far you have seen following ideas. First idea, you understood what do you mean by Ohm's law. You understood that resistance is equal to rho into L by A. From this, you agreed upon that resistance is equal to 1 by K into L by A. Resistance is equal to the resistance into K. Kr is equal to L by A, which is called cell constant. Also, you notice that the specific conductance is conductance caused by 1 centimeter cube ions. Molar conductance is conductance caused by electrolyte having 1 mole of all possible ions in any given volume of solution, which is equal to Kv is equal to K into 1000 by molarity. Molar conductance at equivalent conductance is equal to K into 1000 by normality. Molar conductance is equal to N factor into equivalent conductance. In a Wheatstone-Bridge formula, P by Q is equal to R by S at a null point. We also notice that molar conductance at concentration C is equal to molar conductance at infinite dilution minus V root C. V is a constant. It is called Arrhenius relation. Arrhenius relationship is valid for strong electrolytes. The variation is less if it is a bivalent electrolyte. For a weak electrolyte, the variation of concentration square root and molar conductance is not a straight line. The degree of dissociation of weak electrolyte is given by molar conductance at concentration C by molar conductance at infinite dilution. Always C alpha for any weak electrolyte like acetic acid gives H plus ion concentration. C alpha square for any such weak acid can give Ka value. Knowledge of alpha is very important. To know alpha, you should know molar conductance at infinite dilution. For a strong electrolyte, the molar conductance at infinite dilution can be known by extrapolating this graph. For a weak electrolyte like acetic acid, it is of no use. Kohlrausch law says that according to Kohlrausch law, the molar conductance at infinite dilution of any electrolyte like NaCl is equal to molar conductance at infinite dilution of Na plus molar conductance at infinite dilution of Cl minus. For barium chloride, the molar conductance at infinite dilution is equal to molar conductance at infinite dilution of barium ions plus 2 into molar conductance at infinite dilution of chloride ions. The molar conductance at infinite dilution is an additive property. For example, yes, these are some relations which we have discussed. In this topic called electrochemistry, we have seen some cells where electric current is generated by a spontaneous reaction. We call them as linear cells. These cells are represented through a notation. In the notation, left side fellow is the loser of electron, right side fellow is the gainer of electron. And the ability to lose or gain electrons is measured using a sheet. Always we notice that hydrogen electrode potential is taken as 0. Really, it is not 0. You have taken it as 0. The hydrogen electrode potential varies if you vary the pH. The hydrogen electrode potential is given by minus of 0.059 into pH. The useful energy obtained in any battery is given by minus energy. The cell potential is related to equilibrium constants. When a cell is connected to external circuit, if the external voltage is equal to the voltage generated by cell, then the reactions will stand still. If the external voltage is more than the cell voltage, Then at cathode, instead of reduction, there happens oxidation. At anode, there happens reduction, reverse. If the external voltage is less, or if there is no external voltage, then in any given cell, always at anode there is oxidation loss of electron. Always at cathode there is reduction gain of electron. In this way, we have found out how to find the cell potentials. If you arrange the electrodes in the order of their increasing order of electrode potentials, we call it as electrochemical series. The fellow with more negative electrode potential is a loser of electron, that is called reducing agent. Lithium is a universal reducing agent. Fluorine is a universal gaining agent. We have seen that, how to work out a cell. From there, we also have seen Nernst equation. We also have seen the temperature coefficient of a cell potential. We understood the difference between electrolytic cells, electrochemical cells. We understood Faraday's laws. We also have seen how the conductance of an electrolyte can be measured. Most importantly, you have seen what is called Kohlrausch law. These are the ideas so far we have shared. For your examination the weekend, you can have problems related to Kohlrausch law, problems related to conductance, modal conductance, equivalent conductance, problems related to specific conductance, problems related to Faraday's law, so on. Tomorrow we are focusing only on problems. Also, I try to upload one YouTube video based on problems, only problems. So this is the overall idea. I hope you understood 0.1% at least. Now I will unmute with so that we can speak for a minute. Though one gentleman is very interested to speak unparliamentary language, I have no comment. It is up to him. Okay, sir. He tries to become important by using unparliamentary language. That's fine. People are different kinds. It's okay. So now I am going to facilitate you to speak. Okay. How to do it? Yep. I am permitting you to unmute. Now you can give me your comments about this topic.
Understood.
Clear, sir.
Yes, sir?
Understood,
It's
sir.
clear, sir.
Sir, please explain ionic mobility once.
Just ionic mobility is a quantity you get by dividing the given conductance of an ion with 96,500. Because equivalence conductance is observed for passage of 1 Faraday charge. So if you are saying 1 Faraday is 96,500 coulombs, naturally the measured conductance divided by 96,500 will give you the conductance observed for maintenance of just 1 coulomb charge. How nicely a particular ion can move when 1 coulomb charge is passed is called ionic mobility. So I want you to kindly support this by reading textbook. By and large, tomorrow I will be doing problems, and day after tomorrow, if there is a class, we will be reading the textbook together. You have to read the textbook and you have to do problems. Okay? So tomorrow I want to take up problems. My target is to do 10 problems tomorrow. Can we do, sir?
Yes.
Yes, sir.
Yes, sir.
In physics class, how many problems you do?
Sir, 5 to 10.
Who is that boy talking? Can you tell me his name?
Sir,
Hello?
sir, make me host.
What is the name of this gentleman? Yeah, I identified. I have removed him. Thank you. Yes, sir.
Sir, one YouTube video also you make, sir, on today's class.
I try to make, but I will allow you to record. From tomorrow onwards, I want somebody to record my lectures.
Okay.
So that I give this task to somebody. Somebody will record the lectures so that you can upload my lecture in the YouTube. You can watch in the times.
Yes.
They will upload, sir.
Sir, make me host. Sir, make me host.
Hello.
Yes, sir.
Yes, sir.
Mr. Kazim is there in the meeting.
Yes, sir, he is. Please make
Sir,
sure.
Mr.
make
Kazim,
make
Sir,
me
you
host.
can
Make me
him
host, sir.
you want me to make you host?
Yes, sir. Host or
Can make
co-host.
Kazim sir also.
I made Kazim as a host, okay? Hello, Kazim.
Yes, sir. It's done.
Mr. Kazim, one gentleman is very, enthusiastic, and just see to it that that man enthusiasm is minimized. Okay. Okay, sir. So tomorrow our plan is to do 10 problems minimum. Every student should learn those problems. Number 2, our syllabus is this weekend batteries I am not putting, but rest of the syllabus like Faraday's laws, like Coulom's law, like molar conductance, specific conductance, and also the Nernst equation, cell potential, etc. Tomorrow we have a very good exercise on that. 10 problems is our target. Also, somebody wanted me to make a video on something. What they want, sir, on what I should make?
So on today's class, briefly, can you make?
Today class, actually, next class onwards, I am asking somebody to record the lectures. They will be doing it. Don't worry. Today's lecture, I try to make a YouTube video. Don't worry. Okay. Any more doubts?
No doubt, sir.
Thank you very much for staying with me. I hope you enjoyed the class. Tomorrow we'll be meeting again.
Thank you, sir. Bye.